Noon changes time all the time. Every day, the sun rises and then sets. When the sun is at the highest point in the sky, we call that noon, solar noon. Solar noon is not the same time every day. In Bogota, solar noon is at 12 o'clock on January 2nd, but in February, it moves to 12:10, and in November, it moves to 11:39. Solar noon changes time throughout the whole year, and so it's not a great way of measuring time. Before clocks were invented, people used sundials. They measured time using the sun. But it wasn't very accurate, and they knew it. Even the ancient Greeks knew it was inaccurate. By the way, have you ever wondered why clocks spin clockwise? It's because they were designed to mimic sundials, and that's how sundials spin in the northern hemisphere. The weird behavior of solar noon explains a weird fact about winter solstice. As winter approaches, the days get shorter. Sunrise comes later and sunset comes earlier. But at the same time, solar noon is shifting later in the day, along with sunrise and sunset. In Bogota, the shortest day of the year is December 21st, but the earliest sunset is actually a month earlier, and the latest sunrise is a month later. The time between two solar noons is called the apparent solar day. The apparent day changes length throughout the year, so our clocks are not based on that. Instead, we take the average apparent day, the average time between two noons, to give us the average or mean solar day. That's what our clocks are based on. Every day is the same length for us, even as the length of the apparent day is changing. What is causing this change? There are two factors that cause the apparent day to change. The first is that the Earth's axis is tilted. The second is that the Earth's orbit is not a perfect circle, and so the Earth moves at different speeds at different times of the year. To understand these effects, we need to understand how the sun moves across the sky. We need to give the sky a coordinate system. Now, the best coordinate system for us is the stars. We will use celestial coordinates based on star positions. The stars are a perfect guide for us because they don't move. They're so far away that they stay in place even as the Earth twirls around the solar system. Inside the solar system, the objects here are mostly all on a single plane. That includes the sun, the moon, the Earth, and all the planets. They're all just about on the exact same plane. This plane cuts through the sky. Let's imagine the sky as a giant sphere. This plane cuts through the sphere at a circle, and we call this circle the ecliptic. All these objects in the solar system, they always appear on the ecliptic because they're all on the same plane. So we always see the moon and all the planets on this giant circle in the sky called the ecliptic. Also along the ecliptic are 12 famous star constellations called the zodiac. Now the sun is on the ecliptic, and it goes around the ecliptic once per year. That's actually because the Earth is going around the sun once per year. The Earth orbits the sun at roughly constant speed, and that means the sun goes around the ecliptic at roughly a constant speed. We'll see later that this is an approximation. The speed slightly changes, but don't worry about that now. Let's get back to talking about sunrises, noons, and sunsets. Every day the sun rises, peaks at noon, and then sets. The sun appears higher in the sky when you're facing towards it. When you're most directly facing the sun, that's solar noon. It happens at the same time for everyone at the same longitude. Whenever a line of longitude crosses the sun's position, it's facing towards the sun, and it's solar noon there. Now let's calculate the time between two noons. That's the length of a solar day. The Earth is spinning. For it to spin 360 degrees, it takes 23 hours and 56 minutes, not 24 hours. That's because the Earth isn't just spinning, it's also orbiting the sun. So to get back to solar noon, the Earth needs to rotate another 4 minutes to make up for its orbit around the sun. Let's look at this again in celestial coordinates. The Earth takes 23 hours and 56 minutes to spin 360 degrees. But during that time, the Sun is moving along the ecliptic. It takes a year to fully cycle around the ecliptic. So in a day, the Sun will move 1/365th of a cycle. For the Earth to catch up to the Sun, it needs to do another 1/365th of a rotation. So that explains the extra 4 minutes needed to make a 24-hour day. 23 hours and 56 minutes divided by 360 to 5 equals 4 minutes. The Sun's motion around the ecliptic, that explains the difference between the time it takes the Earth to fully rotate and the length of a day. But it's more complicated than that, because the Earth is tilted. The Earth's rotation is tilted away from the ecliptic. The Earth rotates along lines of latitude parallel to the equator. They're not parallel to the ecliptic. It's tilted. The Earth orbits in the ecliptic plane, but it rotates along the equator in a different tilted plane. In March, the Sun is here on the celestial equator. Over a day, it moves about 1 degree around the ecliptic. How far must the Earth rotate to catch up? How far must this line of longitude rotate? It's less than 1 degree. Earth is rotating to the east, while the Sun is moving northeast. For the Earth to line up with the Sun again, the Earth doesn't need to rotate a full degree. It only needs to rotate 9/10 of the degree. So the time between solar noons, the length of an apparent day, is shorter in March. In June, the Sun moves to the north, and the apparent days get longer. When the Sun is here, what happens when the Sun moves 1 degree? Well, the Earth needs to rotate more than 1 degree to catch up. Before, the Sun was moving northeast, but now the Sun is moving purely east. And notice something else. We measure the Earth's rotation along lines of longitude, and these lines are spaced far apart at the equator and get closer together as we move north. This is the key to understanding why the days get longer in June. To make this effect more obvious, let's exaggerate the tilt of the Earth. So this will tilt the Sun's path to the north. Notice we're not changing how far the Sun moves. As the Sun path moves north, the Sun crosses more lines of longitude. And this means that the Earth must rotate more to catch up with it. So the apparent solar days are longer in June. Now, in reality, the Earth is not tilted this far, so the effect is not this big, but the apparent solar days are longer in June. In September, the Sun moves back south towards the equator. It's now moving southeast. The Earth rotates less to catch up, and the apparent days are shorter. The Sun then moves to the south, and the apparent days get longer in December, and then shorter in March. So the tilt of the Earth causes the days to get longer in the summer and winter, and shorter in the spring and fall. But there's another effect that changes the length of an apparent day. The Earth is not orbiting at a constant speed. The Earth's orbit is not a circle, it's an ellipse. The Earth is closest to the Sun in January. That doesn't stop winter from arriving in the north. Winter arrives because the Sun has moved to the south. As the Earth gets closer to the Sun, it travels faster. Just like if you drop a ball, as the ball falls towards the Earth, it travels faster. You are transferring potential energy into kinetic energy. The same thing happens when the Earth gets closer to the Sun. It speeds up. It's moving fastest in January because that's when the Earth is closest to the Sun. As the Earth moves faster, what we see from our perspective is that the Sun is moving faster along the ecliptic. As the Sun moves faster, the Earth must rotate more to catch up, and that means the apparent days are longer. That's what happens in January. Now in July, the Earth orbits more slowly. The Sun moves more slowly along the ecliptic. The Earth doesn't need to rotate as far, and so the apparent days are shorter in July. I've now explained the two factors that change the length of time between two solar noons. The tilt makes the days longer in the summer and winter and shorter in the spring and fall. The Earth's elliptical orbit makes the days longer in January and shorter in July. Combining these two effects gives us the length of an apparent day and explains why it changes throughout the year.
For more astronomical videos, please click to subscribe.